I'm Jason, and I'm going to talk about projecting quantum computational advantage versus classical state-of-the-art. So this is basically asking the question, the quantum computers we have now or we might have in the near future, when are they going to provide advantage and for what application against the very best classical state-of-the-art software and hardware? So first I have to say, what is quantum computing? I'm not going to be able to do that in a slide or this talk, but I do want to highlight a few important things that I think can help us to better understand where things are right now and where they'll be going. So what is quantum computing? Okay, so we start with a classical bit, a C bit, and it can be in one of two states, only one of two states. A qubit is kind of like a classical bit, but it can be in the superposition of these two states. Okay, so that already brings the weirdness to the table. So another, going further, so this is the idea of superposition, and this is very important, but I'm going to skip over that and say, when we bring qubits together, we can entangle them. And what this does is it produces states that grow exponentially in the number of qubits. So if I have 2 qubits and I entangle them, I have 4 states, 4 computational states I could do computation on. If I have 3 qubits, 8 states, and by the time you get to 53 qubits, which isn't a very large number of qubits, you're at 2 to the 53 states, and this is the petascale. So what happened recently was this research group here did simulations of a quantum computer of about that size on our very best classical supercomputer. And they did this to establish the so-called quantum supremacy frontier with this simulation. So you can see that the potential is there. You don't really need a very large machine, and you're already at the sort of capacity of our best supercomputers. This doesn't tell the entire story. This is not the only thing that leads to performance. There's all kinds of engineering challenges, but this gives you some indication. Okay, so what I'm really talking about in this talk is universal gate quantum computing, and so this is a particular flavor of quantum computing where we have these qubits, and we want to put them together and entangle them, and then we want to do useful operations on those qubits to execute some algorithm. So this is a very challenging engineering task right now in identifying applications at the highest level, specifying algorithms in some high-level quantum language that replace in those applications the things, the computational tasks you want to replace, and then taking that representation through various intermediate representations until finally you're down on QPUs. And this is all a software engineering challenge at every layer of this stack. And you've got to get all this right to ultimately leverage this potential power that we were talking about in the previous slide. And this is all very new technology, and there's very few people in the world that can do it. So there's some estimates that there's 25,000 people in the world that can do deep learning in an expert way. And similar estimates for quantum computing suggest maybe there's 1,000 people in the world that can do this. So I think that the technology is changing, there's potential there, but we need help at all layers of the stack, of the software engineering stack. Okay. So why quantum computing? Well, I gave some taste, some flavor of it with the petascale comment. Now, we see that actually that paper was related to a recent leak, if any of you have seen this in the press, that quantum supremacy may have just been demonstrated. Okay, so quantum supremacy is a little bit of an overhyped term. It gives the impression that when this is achieved, the quantum computers will take over everything and we'll be using them to do everything that's hard, and that's not the truth. Quantum supremacy is simply a narrow but well-defined computational task that we can run on available quantum processors now and our best supercomputers, and we show that the quantum processor ends up outperforming them on this task at some point. This is all going to be criticized and reviewed in the literature in the coming years and so forth. But even if it was achieved, and even if it can be justified, it's really just like we built the engine of the race car and we turned it on and it's running. We really haven't done anything very useful with it. We need to package the engine, fully scale the computer, put it into a race car so we can drive around a track and do something useful with it. So that's what our research is focused on, finding quantum advantage, which is really just the same as supremacy, but going one step further, we want advantage on practical problems. We want this stuff to be worth the cost of investment and all that. Okay, so I'll come back to that a little later in the talk. Okay, so maybe supremacy was demonstrated. So what can we do with quantum computers? Well, another recent paper that's very interesting with respect to cryptography was this following paper, how to factor 2048-bit RSA integers in 8 hours using 20 million noisy qubits. What's important about that? basically this paper goes through a very detailed analysis from top to bottom, the application, running Shor's algorithm to break RSA, all the way down to the specification of the microarchitecture, a qubit count, 20 million, and a noise level, noise characteristics of that device. What this all means at the end of the day is that we're now at this stage in the technology where we can make this prediction that if we keep going, let's say, along the path that we are with the progress of technology in the ways that it is, that maybe in 20-year time frame, we'll have a machine that is 20 million qubits with the right noise that can execute this algorithm. Okay, but that's a long time from now. We don't want to wait around for 20 years to run Shor's algorithm. But it gives you an idea about the tension that exists between predicting advantage for applications but not wanting to wait 20 years to use the technology. Also important is that even if you did have this capability, NIST is already reviewing post-quantum encryption protocols, which are resilient, can't be broken by a quantum computer. So it's kind of a moot point in some sense. But this is another example of quantum advantage, at least projected quantum advantage. So what other applications can we find this kind of quantum advantage for? So that's another important question that we're asking. Okay, so that's all in 20 years, and that's a fully scaled, fault-tolerant quantum computer. So what do we do until then? And that's like 20 years from now, let's say. So this is what we talk about in the NISQ era, quantum computing in the NISQ era. NISQ stands for Noisy Intermediate Scale Quantum Computers, and they're characterized by having a small number of qubits. So over here is like some different designs of QPU chips, the way which we can lay out qubits, their connectivity to each other, and so forth. And the other thing there are a small number of qubits and an unsure architectural design is these qubits are noisy. So they don't keep their state forever. They don't persist. Noise from the environment and from other qubits decoheres their state and ruins the computation. So on the right here is error rates of the gates which operate between qubit pairs, so 2 and 3 and 3 and 16 and so forth. And you can see how much variation there is just by the hour of day in the error rates, and also between the different gates themselves. So this is a very distinct challenge in quantum computing, which just adds to the complexity of the whole process. So the challenge is, now we have our software stack, and that thing is still evolving, right? The hardware underneath is moving, the architectural parameters. We need those architectural parameters. They're crucial to pipe back up into the software design process so that it can be incorporated in the optimization of the software. And of course, we still have the issue of finding applications. So this is giving me maybe a better sense of how difficult things are from a software engineering standpoint in this technology. The other thing that's important is one has to utilize this methodology here to produce the very best code you can run on our limited QPUs we have today, or maybe you can send it to simulation and imagine the kind of QPUs we could have in the next 5 years or so. But to be sure about quantum advantage, you really need benchmarks, and you really need benchmarks against the absolute best that classical computing brings to the table. So we approached this project by first starting with our expertise in classical high-performance computing. So for example, on DARPA software-defined hardware, where we source, this project seeks to source the hard problems within the DoD in different domains like combinatorial optimization, graph analytics, and AI machine learning, and then find the very best software, classically, and hardware, or use that software to define new hardware which would run those problems efficiently. So we draw from that project in these domains to produce the very best classical benchmarks we can. And then we judge our QPUs, the ones that exist today or the ones that could exist, against those benchmarks. So what we're trying to do is be as honest as we can be from a performance standpoint. It's like, when are these QPUs for a given application is actually going to provide advantage? And I have had results in the poster, during the poster session, but I realized that was yesterday. If anyone in the crowd is interested in more detail than this, I can provide it. So let's see. Good. So quantum QPUs have a tall task ahead of them. Integrated circuits in classical computing is a 60-plus year technology, both in hardware and maybe more importantly, software, right? So we're building this quantum software, and that's hard, but we're also in the very infant stages of quantum algorithm design, right? So I think this all comes together, and this is basically the test apparatus that we use for our research. Okay, so what does this mean for the SCI and the DoD in the future? Okay, so I think what's almost certainly the case is that quantum computing, it has, and it will have many forms. So there's not going to be one quantum architecture or one provider that dominates the market. So right now, I was talking about universal gate quantum computing, which has subsets, superconducting qubits, trapped ions. But the problem is that when we're trying to figure out our applications, we also have to decide on architectures. Which of these architectures are going to be the ones which are best for my application? Once I make that selection, then we have subsets within a given architecture, and each of them has their own full stack ecosystems of software and hardware. So this makes the whole ordeal particularly challenging because over here on the right side, with this full stack, we have things changing. So that matriculates back up and informs application selection. So you see this is kind of a tied system. But this is really the approach you want to take when you're trying to decide as an organization when and where will I use quantum computing, what applications and what specific architectures and providers should I use to tackle those problems. Because that's one thing. And the other thing I think I already harped on, which is that there seems to be very, very few people in the world that can do this. And I think that certainly has to change because we need to get more creative. Mentioned hardware, mentioned software. I think software is a major focus, or should be. We have only a few decades of algorithmic development in quantum computing. And I certainly think that this kind of expertise, this small number of people in the world that have this expertise, certainly plays into that, or lack of progress there. So to this end, for this research project at the SCI and CMU, we created a quantum hub, which is a Jupyter Hub server which connects users to all the different quantum computing software stacks that we play with for different architectures. It connects them to actual QPUs in the back end. All these companies making quantum processors, a good deal of them provide cloud access to their machines, so you can do benchmarking. And it also brings together a community at CMU, which is covering applications in these domains: the electrical and computer engineering department, physics, computer science, and material science. So we would like to grow this thing here at CMU and try and continue attacking these problems, tremendous number of them at the software engineering level. And I think that might be it, yes. So how much time was that? Good. Questions? Does anyone want to ask any questions? Sure.
So I'd like to understand, where are we today in terms of logical qubits? How many physical qubits are needed to make a logical qubit? And how many really logical qubits do we need to do something useful?
Right, so, okay, so he asked the question, or everyone heard, sorry. He asked about logical and physical qubits, and so this is really about error correction. So the work that we're doing in this NISQ era, we work with algorithms that don't require any error correction, active error correction. They want to use all of the physical qubits as operational qubits. In the long run, resource estimates, it depends on the problem and the error correction code, but resource estimates could be for every one logical qubit, you'll need at least 10, maybe 100 more error correction qubits. That's why this 20 million noisy qubits number, like 2048 is 2048 qubits to store the number, but then we need all those rest of those qubits to operate as error correction. And the error correction is what allows you to run for 8 hours. Right now, you can run a computation for like 100 microseconds. So it's a huge gap. And you want to use error mitigation, so some techniques that don't require you use any qubits as error correction, but I'll mitigate it some other way, like injecting more noise on purpose or in some controlled way, something like that. Questions?
Yeah, so related to that last question, you started off by talking about entanglement, being able to get you more logical, in order to get you more logical capability. So I try and put those two together.
Oh, so the qubit entangling thing is about, if I entangle these qubits, I produce a number of computational states that I could compute on that grows like exponentially. So when you get to 53 qubits, though, there will be a computational state space with that many coefficients.
Okay.
But the problem is the noise. So what, you can make that, but the thing decoheres in 100 microseconds, so, yeah. Any other questions? Oh, forward. Keep going. Which slide? Oh, the website. Oh, yeah, that one. Oh, yeah. You can contact us to get accounts. Yeah, if you want access to this, just send me a message. I think my contact information is in the, yeah. Anyone else? Thank you.